Hey there, fellow space enthusiasts. Ready for another deep dive? Today we're taking a look at black holes and
Ooh,
how they shape the universe around them.
black holes. Yeah, so fascinating, right?
Absolutely. And, we always hear about them gobbling up matter and light and everything, but
Yeah.
there's a lot more to the story, right?
There is. There's a lot more to the story. They're not just cosmic vacuum planners. They're dynamic objects.
Yeah. So we're going to be talking today about a recent discovery published in Nature. And this
Well,
discovery is about a structure called Porphyrion.
Porphyrion. Okay.
Yeah, have you heard about this? 7 megaparsecs long.
Wow. That's huge. I mean,
That's big, right?
that's bigger than huge.
Yeah. So to put that in perspective, imagine a cosmic void, like a giant empty bubble in the universe.
Right.
Porphyrion stretches across roughly 66% the radius of one of these voids.
That's really putting it into scale. I can
Yeah.
I can appreciate that.
So how did a black hole create this massive structure?
That's a great question.
Yeah,
And that's what we're going to unpack today.
right. And luckily, I've got an expert here with me to guide us through all this.
I'm excited to be here. This is it's going to be fun.
Yeah. So let's start with the basics.
Okay.
We know black hole have this immense gravitational pull, but they also launch these powerful jets. What are those?
Yeah. So you've got supermassive black holes sitting at the centers of galaxies, right?
Okay.
For feasting on gas and dust.
Right.
But not all of that material falls in. Some of it gets channeled and
Perfect.
accelerated outwards, forming these incredible jets of high-energy particles and magnetic fields.
So it's like a pressure cooker.
Yeah, you could think of it like a cosmic pressure cooker.
Okay.
As the black hole devours matter, it releases this powerful stream of energy back out into the universe.
So it's not just a one-way street with still falling in.
No. It's a cosmic engine. Matter goes in, energy blasts out.
Oh, I like that.
It's pretty cool, right?
Okay, so those are the jets, but why are they important?
Oh, they're super important. They affect how galaxies evolve. They heat up the gas between galaxies, what we call the intergalactic medium, the IGM,
Right?
and they transport energy across mind-boggling distances. It's just incredible.
Wow, that's a lot of impact.
It is.
So this is like a giant cosmic energy transfer system.
Exactly.
That's pretty cool.
Yeah.
Okay, so back to Porphyrion. How did scientists even find this thing?
Oh, this is a great story. They used the International LOFAR telescope.
Okay.
It's a massive network of radio telescopes
Okay.
spread across Europe. It's like having a giant ear to the cosmos, listening to these faint whispers from the distant universe.
So they're tuning into radio waves, not just looking for visible light.
Exactly. And those radio waves, they come from particle in the jet as they interact with magnetic fields.
Okay.
It's kind of like how a radio station transmits signals, but this signal of coming from a jet blasting out of a black hole billions of years ago.
Okay, that's a lot to process.
It is. It is.
So they detect these radio waves coming from Porphyrion. How do they know it's so incredibly big?
Well, they can analyze the patterns of those radio waves.
Right.
And by doing that, they can piece together the structure, kind of like putting together a jigsaw puzzle.
Oh, okay.
Right.
Yeah, I like that.
And in the case of Porphyrion, the puzzle pieces revealed the structure of astonishing size, 7 megaparsecs.
Wow. That's like finding a dinosaur bone,
I know.
the size of a mountain range. It's incredible.
It's hard to even picture, right?
Yeah, it's
Yeah.
hard to wrap your head around. And this has been out there for billions of years.
Billions of years.
Wow.
Scientists estimate it formed like 4.4 to 6.3 billion years after the Big Bang.
Wow. So this black hole's been blasting out this jet, sculpting this colossal structure for a very long time.
It's a long-term construction project.
Yeah.
It's pretty incredible.
Okay. So the Nature article describes this complex structure: lobes, jets, hotspots, backflow.
Okay,
Can you walk us through it?
sure. So think of it like a map,
Okay.
right, with
Yeah.
the different landmarks.
Okay.
At the northern end, you have the northern lobe, this massive cloud of gas,
Okay.
energized by the jet. That lobe is connected to the central core where the black hole lives
Right.
by a jet of material.
Right.
And extending southward from the core is another jet,
Mhm.
culminating in a really complex structure with an inner hotspot, an outer hotspot, and backflow.
Okay. So you've got this central black hole
Yep.
shooting out these jets,
Yeah.
like beams of energy.
Exactly.
And then you get these lobes at the ends.
The lobes, yeah, those are like exhaust plumes of a black hole jet engine.
Oh, okay. Okay.
Right, the regions where the jet has interacted with the intergalactic medium spreading out.
Okay. And the hotspots.
Oh, the hot spots.
Yeah, it sounds like a cosmic weather report.
Well, yeah, it's like the jet is slamming into the surrounding gas,
Okay.
creating shock waves,
Oh, wow.
generating powerful radio emissions. Imagine like a supersonic jet breaking the sound barrier.
Oh, okay.
You get that sonic boom.
Yeah, yeah.
These hotspots are like cosmic sonic booms.
Wow,
I know.
that's pretty intense. And the backflow?
Backflow, so that's material that's deflected back towards the core.
So like a boomerang.
A cosmic boomerang.
Okay.
Pretty cool, right?
It's really fascinating how astronomers can identify all this from billions of light years away.
I know, it's amazing, right?
Yeah,
They use radio astronomy so they can detect and analyze radio waves.
right.
And to get more detail, they even use something called VLBI data.
Okay.
Very long baseline interferometry. It's like having a telescope as big as the Earth.
That's pretty big.
It is.
Okay, so they pinpointed the host galaxy for Porphyrion
They did.
using the Keck Observatory, so they figured out exactly where this is.
They did. They figured out exactly where this black hole is, how far away it is.
So they know exactly which black hole is responsive.
It's a massive elliptical galaxy
Oh.
harboring this supermassive black hole at its center.
Wow.
And they analyzed the light from this galaxy. They figured out it's about 6.3 billion light years away.
So back in the early universe.
Back in the early universe when galaxies were forming and evolving super rapidly.
Wow. Okay, so we've got this massive structure, 7 megaparsecs, formed billions of years ago, back when the universe was a much more dynamic place.
It was a wild time back then.
Yeah. Okay, but here's what's puzzling to me.
Okay.
These jets remain stable
Right.
over this vast distance
Yeah.
and timescale.
That's surprising.
That should happen, right?
Yeah, it is surprising. You wouldn't think they could stay animated, stay focused for
Yeah.
that long.
It's like trying to shoot a water gun across a football field
I know, right?
and expecting the stream to stay straight.
Exactly. How did Porphyrion's jet stay focused for billions of years and create this structure?
Yeah. It doesn't make sense.
It's a mystery. It challenges what we know about black hole physics,
Right.
the properties of the intergalactic medium.
So the universe is throwing us a bit of a curveball here.
It is.
It's showing us that
Big time.
maybe we don't understand these things as well as we thought we did.
It's exciting.
Yeah, it's definitely exciting.
It's a challenge.
Okay, so how are they trying to explain Porphyrion's stability? What are they looking at?
So there's a concept called radiative efficiency, or R.
Okay.
It plays a big role in how these jets form.
Okay.
RAGN, though they're active galactic nuclei, they're super efficient at converting the
Right.
gravitational energy from infalling matter into
Right.
radiation. They're like high-performance engines,
Oh, okay.
converting matter into energy
Right.
with crazy efficiency.
So the more efficient they are, the more powerful and focused the jets.
Exactly. And Porphyrion, we think it's powered by an RAGN. Now contrast that with
Yeah.
RAGN, radiatively inefficient.
Yeah.
They're not as efficient.
Right.
And what's interesting, all the previously known record-holding outflows, those massive structures we've seen,
Right.
they've been fueled by RAGN in recent time.
Okay, so Porphyrion's different.
Yeah, Porphyrion is an outlier.
It's powered by an RAGN,
Yes.
and it existed in the early universe.
A long time ago. And that makes this a big deal. It suggests that REAGN, maybe they were crucial in shaping the early universe.
Wow.
Right.
Okay, so this one discovery could rewrite our understanding of the early universe.
Potentially, yeah. It's pretty exciting.
But simulating these massive jets, like the ones from Porphyrion,
Right.
that must be incredibly difficult.
It is. It really is. The scale, the complexity, it requires enormous computing power, fancy algorithms.
Right.
To model Porphyrion's jets accurately, we'd need a spatiotemporal grid, basically a 4D map of space and time.
Okay.
That's like 100 times more detailed than what we can do right now.
So even with all our tech, we're still limited.
We are. The cosmos is just so vast.
It's humbling.
It is humbling. But we can still learn from Porphyrion.
Right.
It gives us this observational window into Jeff physics that we can't explore with simulations right now.
So it's like a glimpse into a hidden world.
It is one that challenges our models,
Yeah.
inspires us to push our understanding further.
I like that. Okay, so let's talk about where Porphyrion fits in the grand cosmic web. We know the universe isn't just randomly scattered galaxies.
No, it's not.
It's this intricate web, right?
Yeah.
Filaments, clusters, voids. So where does Porphyrion fit in all of this?
That is a great question. And based on what we've seen, it seems like Porphyrion is located in a cosmic web filament, specifically probably within a galaxy group.
Galaxy group, so it's hanging out with a few galaxy buddies.
Exactly. It's not alone, but it's not in a massive, crowded cluster.
Interesting. Okay, so what can you tell us about the age of Porphyrion and the energy it's released?
So the team used dynamical modeling
Okay.
to estimate those values.
Right.
And they found Porphyrion is about 1.9 billion years old. Pretty impressive, right?
That's quite old.
It is. And get this. It has injected 7.6 times 10 to the 55 joules of energy into its surroundings.
Okay, that number's so big I can't even
Ah.
fathom it. Can you put that in perspective?
Imagine the energy released by a supernova, one of the most powerful explosions. Now multiply that by 1 billion.
Wow. Okay.
That's starting to get close.
So what happens when a black hole unleashes that much power on its neighborhood?
It changes things. Porphyrion's jets have likely altered the shape of the filament it's in, making the IgM hotter and thicker than it would have been otherwise.
So it's not just creating this massive structure, it's changing the environment.
Exactly. It's a cosmic sculptor shaping the universe.
I like that.
Yeah.
Okay, so if Porphyrion can do all this, what about all the other black holes out there?
Ooh, good question.
What else is hidden?
The discovery of Porphyrion suggests there might be a whole population of even bigger outflows out there, hidden because they're so faint and distant.
Wow. So we've only scratched the surface.
We've just scratched the surface. This is a hidden universe of giant black hole outflows.
That's incredible.
It is.
Okay, so Porphyrion's not just a one-off, it's a potential game changer for our understanding of how galaxies evolve.
It is. It changes how we think about AGN feedback in galaxy evolution,
Right.
and even the evolution of the cosmic web itself.
Wow, okay, well, we've covered a lot today, exploring Porphyrion and the power of black holes, but there's so much more to unravel. We'll be back in a moment to delve deeper into the mysteries of this cosmic giant. Stay tuned.
Can't wait.
Me too.
This is great.
All right, we'll be right back.
Okay. It really is mind-boggling to think that something that huge has been out there this whole time.
It really makes you wonder what else is out there, hiding in plain sight.
I know, right? We were just talking about that hidden population of giant black hole outflows.
Right, and if Porphyrion's just the tip of the iceberg,
Yeah.
what does that tell us about the universe as a whole?
Well, I think it paints a picture of a universe that's much more dynamic
Right.
and energetic than we might have thought.
Okay.
You know, these outflows with their incredible power,
Yep.
they could be playing a much bigger role in shaping things than we ever imagined.
Right, right. It's almost like we've been looking at the universe
Yes.
through this tiny little window,
Exactly.
and then Porphyrion comes along
Yeah.
and blows the whole thing wide open.
It's a great analogy.
Yeah.
It really is. Like, we've been focused on the trees, and now we can see the whole forest.
Yeah, yeah. Okay, so this isn't just about one cool object. It's about changing our whole understanding of how the universe works.
Exactly. It could change how we think about how galaxies evolve.
Right,
How the gas between galaxies gets heated up and gets all those elements.
right, right.
And even how the cosmic web forms.
Wow.
And evolves over time.
Okay, it's like we found this missing piece
Yeah, like a jigsaw puzzle.
of a giant cosmic jigsaw puzzle, and now we need to figure out where it goes.
Exactly. And that's what's so exciting,
Uh-huh.
trying to piece it all together and seeing what picture emerges.
Okay, speaking of puzzles, let's go back to Porphyrion for a sec. The Nature article talks about its radio emissions,
Okay.
and apparently different parts of it emit radio waves at different frequencies. What's up with that?
Oh, that's a great point. So the radio spectrum of Porphyrion is like a fingerprint. It tells us about what's happening inside,
Okay,
the physical processes in the outflow.
so it's like listening to a cosmic radio station,
Yes,
and each frequency tells part of the story.
exactly. And the message we're getting from Porphyrion, it's pretty complex.
Okay,
For example, they found that the core, where the black hole is, it emits radio waves with a flat spectrum.
okay.
And that suggests that something called synchrotron self-absorption is happening.
Synchrotron self-absorption, that sounds pretty complicated.
It does sound complicated, but it's actually not that bad.
Okay.
Think about a microphone feedback loop.
Oh, yeah, yeah.
You know that screeching sound?
Right, right,
Happens when the sound from the speakers gets picked up by the microphone.
right, and amplified.
Exactly, and it creates this runaway loop. Synchrotron self-absorption is kind of like that.
Okay.
The radio waves are getting absorbed by the electrons that are making them.
So it's like a feedback loop
Yeah.
inside the black hole's core.
Right in the core. And by studying that feedback loop, we can actually learn about the density and energy of the electrons in there.
Wow.
It tells us about that extreme environment.
Okay, so the core has a flat spectrum.
Yeah.
What about the other parts of Porphyrion? Are they different?
They are different. They found that the southern tip, where the jet's slamming into the intergalactic medium,
Right.
it has a steeper radio spectrum.
Okay, so what does that mean?
That means the radio emissions at higher frequencies are weaker
Okay.
than the lower frequencies.
So different parts of Porphyrion
Yeah,
are like different instruments in an orchestra,
that's a great way to think about it.
playing their own tunes,
Yes, and just like a conductor listens to each instrument,
right?
astronomers study these different frequencies to understand what's happening.
Okay.
The speaker spectrum at the southern tip tells us that the electrons are losing energy
Okay.
as they travel out and interact with the environment.
Right.
It's like a runner slowing down near the finish line.
Yeah. Yeah. Okay, I get that. So by analyzing these little changes in the radio emissions,
Exactly.
scientists can get a better picture
They
of
can.
what's going on inside Porphyrion.
It's amazing what we can learn from these faint whispers.
It is. It is.
And it shows how important it is to look at things in different ways, multi-wavelength observations.
Right. Like having a whole toolbox of
Yes,
different instruments.
exactly. And we need all those tools to understand something as complex as porphyrion.
So by combining all that info,
Yeah,
scientists can try to answer those big questions, right?
exactly. Like, how does it stay stable?
Right.
What role does the IgM play?
Right, right,
What are the long-term effects of this powerful outflow?
right. And those are all connected
They are.
to how galaxies and the whole cosmic web evolve over time.
Yes, that's exactly it.
It's like trying to understand the history of a forest.
I love that analogy.
Yeah.
It's perfect.
Just by looking at the rings of one tree.
And just like those growth rings tell us about the climate the tree lived in,
Right, right.
Porphyrion can tell us about the conditions in the early universe.
Wow. Okay. So where does all this leave us? What are the key takeaways here?
Well, I think the main thing is that Porphyrion is incredibly powerful and ancient.
Okay.
It's huge, it's influencing the cosmic web, and it's telling us that there might be others out there even bigger just waiting to be found.
Right, right. It's amazing what we've learned from one object.
It really is.
It really shows the power of observation.
It does. It shows that there's still so much more out there to discover.
And that we still have a lot to learn.
Oh, absolutely. Porphyrion has challenged our assumptions and given us a whole new set of questions to ponder.
Pretty exciting stuff.
It is. It really is.
Okay, so where do we go from here? What's next for astronomers studying Porphyrion and these giant outflows?
Well, I think a big question now is how these outflows affect galaxies and the whole cosmic web.
Right,
We know they're putting out a ton of energy,
right,
but how does that energy affect star formation, galaxy growth,
right.
the distribution of matter on these huge scales?
So it's like a cosmic chain reaction.
Yes, exactly. These outflows are like triggers setting off a whole chain of events across the universe.
Okay,
It's like a giant, complex ecosystem.
wow.
And we're just starting to understand how it all works.
Right, so we need more data, more observations.
We do. We need better telescopes.
Right,
Better simulations.
Yeah.
We need scientists from all different fields to work together.
right, to figure this all out.
It's an exciting time to be an astronomer.
It really is, with new discoveries all the time.
All the time.
Okay, well, we'll be back after a short break to talk about the implications of all this and what it means for the future of astronomy, so stay tuned. Welcome back. We've been talking about black holes, Porphyrion, and their impact on the universe. It's been quite a journey, right?
It really has. Just mind-blowing to think about the scale of it all.
Yeah, Porphyrion has really changed how we think about these things. We used to think those powerful outflows, those jets,
Right.
were just confined to like the areas around galaxies. But now we see they can reach out and shape the cosmic web itself.
It really makes you rethink things. We always thought of black holes as these destructive forces,
Yeah,
just
yeah.
swallowing everything up. But Porphyrion shows us there's a creative side, too.
It's not just about things falling in.
Right.
Where it's also about this incredible amount of energy
Yes.
and matter being blasted out and what that does to everything around it over billions of years.
Exactly. And that makes you wonder, what if this creative force, this shaping of the universe by black holes, is actually way more common than we thought?
That's what I was thinking too. We've been focused on Porphyrion.
Yeah.
But you said earlier that it might be just the tip of the iceberg. If one black hole can create something this massive, imagine all the black holes out there
Right.
over billions of years. It's hard to even imagine.
It's really mind-boggling. It suggests that black holes might be essential architects of the universe.
Architects. So they're not just shaping what's already there.
Right.
They're actually laying the foundation for everything.
That's the idea. They're outflows, they're powerful, but they could also be the reason why galaxies form.
Wow.
Why the space between galaxies gets all those elements needed for stars.
Okay.
And how the cosmic web itself evolved.
That's a huge shift in perspective. It's like we've been studying these little brush strokes
Yeah, I like that.
without realizing they're part of a much bigger picture.
A masterpiece that's still being created.
Right. The universe is always changing and evolving.
It is.
And black holes are a key part of that. It's like a cosmic dance, this back and forth
I know, right?
between creation and destruction,
Yeah.
and order and chaos. And with Porphyrion, we get this front row seat to see it all.
It's amazing, a privilege to be able to study these things and learn from them.
And it shows how much we still don't know. Porphyrion has given us more questions than answers.
It really has.
But that's a good thing.
It is.
It means we have to keep exploring, keep learning.
Absolutely. That's what makes astronomy so exciting, this constant journey of discovery. You never know what you're going to find.
Well, I think that's a great place to wrap up our deep dive into Porphyrion and the power of black holes. It's been a truly mind-blowing experience.
It really has.
If there's another thing we can all take away for this, it's that the universe is full of surprises.
It definitely is.
So to everyone listening out there, keep looking up at the stars, keep asking questions, and never stop being curious about the universe. You never know what amazing discoveries are waiting out there. Until next time.